Hello, welcome back to the DL Software Digital Guide, the one-stop practical guide for DL Software toolkits. This is part of the DL video series that shows you how to use DL more effectively. In this video, I'm going to talk about changing the states of atoms in your molecular system. By default, atoms in a system are allowed to move freely according to the resultant forces experienced by each atom due to the presence of other atoms. These atoms are called free atoms. In addition, the velocities and positions of atoms can be rescaled depending on the type of system ensemble. For instance, atoms' velocities can be rescaled due to the connection of the system model to a thermostat to ensure the system is maintained at a desired temperature. However, depending on the specific requirement of your system, it is possible to redefine the state of an atom and thus restrict the motion of the atom to a different extent that is not due to the chemical forces nor the thermostat experienced by the atom. For instance, we can freeze atom 2 by resetting its velocity v2 to 0 so that the position of the atom will not be updated over the time step. DL allows you to redefine free atoms to one of the following states: atoms with constraint bonds, tethered atoms, frozen atoms, or rigid atoms. I will explain what these states are and show you in details how to define them. Atoms with constraint bonds are the atoms whose motions are subjected to constraint forces in such a way the bonds that are connected to these atoms are maintained at a fixed distance within a tolerance limit. The chemical bonds between two atoms are usually represented by some functional forms such as the harmonic to mimic the bond vibrations. This would be some of the fastest mode of motions in a classical molecular simulation, and the value of time step used in a molecular dynamics simulation must be small enough to account for this. For instance, bonds that are connected to light elements such as the hydrogen atoms will vibrate faster, and thus the value of time step must be small enough to account for this. Normally, this value is in the order of 0.5 femtoseconds. However, if the bond length is fixed, this will effectively remove the fast vibrational motion or the degree of freedoms, and thus the time step can be increased. For instance, if the bond length that contains hydrogen atoms are fixed, the value of time step can be increased to around 2 femtoseconds. This will allow longer time scale to be simulated in a given total number of molecular dynamics steps. In DL Poly, the shake algorithm is used to fix the bond length to within a specified tolerance limit, and this is achieved by applying an additional force to restrict the position of the atom relative to the other. I will now show you how to introduce constraint bonds in the model. We will use the PDB protein structure as an example. This is superoxide dismutase, or SOD1, a protein enzyme that protects cells from oxygen damage. In human and in most other animals, the enzyme exists as a dimer. In the PDB file, the two monomers are labeled as, in capital letters, SOD1 and SOD2 respectively. In DL these are two different molecular groups. This is the DL control file. We will use the OPLS version AAM protein force field model. To use the constraint bond feature, the appropriate master switch option must set to 1. We switch off all other atom states such as the freeze, tether, and rigid body. We then need to inform DL how to set up the constraint bonds in the atom state specification by scrolling further down the control file. The atom state specification is a special segment contained within the control file separated by the hash lines as shown. The segment contains a set of atom state directives that define which atom states will be imposed on which molecular groups of the system. In this example, DL will ignore the freeze, tether, and rigid directives since the master switches for these atom states have been switched off. We will turn our attention to the constraint directive as shown. The directive accepts two parameters, the first being the molecular group to which the bond constraint will be defined. The second parameter is the atom filter key. In this example, the constraint directive specifies that bond constraints will be imposed on atoms belong to the molecular group SOD1. The atom filter key H-bond means only bonds that contain the hydrogen atoms will be constrained. We now run DL-Fill. Once this is completed, we will examine the fill file produced. In the fill file, the SOD1 molecular group contains a total of 1,129 non-hydrogen containing bonds. And there are 1,077 constrained bonds, which were all connected to the hydrogen atoms. For atoms belonged to the SOD2 group, there is no constraint bond, and there are a total of 2,206 bonds in the molecule. In addition to the H-bond filter key, there are other filter keys as shown here. Please consult the DL-Fill menu for more details. Next, we look at the tethered atoms. An atom is said to be tethered when it is connected to a fixed imaginary point F by a spring with a spring constant K. The fixed point F is centered at the atom in the initial configuration before the start of a molecular dynamics run. The point F will be fixed throughout the simulation, while the position of the atom will fluctuate around that point. The procedures to set up tethered atoms are similar to that of constrained bonds. In the control file, the tether master switch must be turned on. Then, the tether directive must be defined in the atom state specification segment. The notable difference would be the tether directive takes 3 parameters instead of 2, and there are more and different filter keys available for the tethered atoms than for the constrained bonds. The filter keys C-alpha and or backbone are only applicable to protein systems. As the name implies, the C-alpha refers to the alpha carbon to which the amino acid side chain is connected. The or backbone filter key refers to the protein backbone that holds a protein together, the alpha carbon, the amide carbon, and the nitrogen atom. The filter called the atom key is the actual atom label to which the tethered spring will be applied. Last but not least, the OR filter key means all the atoms in the molecular group will be tethered. We now use the same SOD1 protein structure as our example. This time, we would like to impose tethered atoms only on the protein backbone atoms that belong to the molecular group SOD2. Note that the energy unit specified here, which is kcal per mole, the same energy unit will be used for the spring constant for tethered atoms. Here, only the tethered option is switched on. This means all other directives except the tethered directive in the atom state specification segment will be ignored. The tethered directives is shown as follows. The spring constant of 100 is set and the unit is kcal per mole per Armstrong square as per the specification of the energy unit in the control file. After running DL-Fill, a set of tethered atoms were defined for the molecular group SOD2 as shown in the fill file. Next, we look at the frozen atoms. As the term implies, frozen atoms means atoms that do not move and the positions are fixed throughout the whole simulations. The way how to set up frozen atoms is the same as that of the tethered atoms, and therefore we will not discuss this in details. To set up frozen atoms, the freeze directive will be used in the atom statement specification section. Example here shows all atoms with the label AO and belonged to the molecular group CLY will be frozen. Finally, we come to the rigid body. A rigid body is considered as a single unit which consists of a group of atoms. The relative positions of atoms within a rigid unit are fixed, and the only degree of freedom is the translational and rotational motions of the whole unit. This means the bond, angle, and dihedral components within the unit will not be considered. The way to define rigid units is a little different than what we have discussed so far. To define a rigid unit, first of all, you would need to list out the individual atoms that made up a rigid unit. A rigid unit must always be defined as a set of atoms contained in a molecule template. After that, in the DLView control file, you need to turn on the master switch for the rigid atoms. Lastly, a rigid directive needs to be issued in the atom state specification section. Unlike other directives, the rigid directive only takes the single parameter, which is the molecular group of the atoms that need to be rigidified. Note also that to define rigid atoms, the user structures must be in the PDB file format. We use a benzene molecule as an example to illustrate how to set up a rigid unit. We see that the 6 aromatic carbon atoms are labeled serially from C1 to C6, and we intend to set up the whole aromatic system as a single rigid unit as shown on the right. Note that the hydrogen atoms are still flexible relative to the rigid ring. The rigid aromatic ring must be defined in the benzene molecule template. This has been defined for the charm general force field CGen-FF as shown here. And this is the example benzene structure in the PDB format. Next, we are going to use DLView to read in this structure to set up the force field model. Note that since no molecular group has been defined in the PDB file, DLView will automatically assign a default name called not defined. This is the control file, and we are going to use charm general force field. In this model setup, we are not going to activate the rigid body assignment by switching the rigid master switch to off. We now run DLView, and after that, we'll inspect the field file produced. As you can see, a charm force field model for a fully flexible benzene molecule has been set up. It has a total of 51 entries for bond interactions, 18 entries for angle, and 24 entries for the dihedral. We will now activate the rigid atom feature. After that, we would need to specify the molecular group to which the rigid atoms would be applied. In this example, it will be the one and only one molecular group called not defined. Notice that a rigid directive has already been defined, perhaps from some previous model setups. DLView will ignore it should the molecular group specified does not match with this model. You can simply delete it or just add another rigid directive for this model setup. Let's run DLView again and then inspect the field file produced and see the difference. You will notice there's a reduction in interaction sets for all components. This is because the rigid body, as defined in the molecule template, has been set up for the aromatic carbon ring, and the relevant internal interactions for the ring is no longer necessary. The rigid body for the ring is defined here. That's it. I hope you enjoyed this video session and become more familiar on how to use DLView. Thank you and goodbye.